Very good morning to you all. Today, we are going to see the left out topics in MIMO system. So far, we have seen in MIMO system, we have seen what is MIMO system, then what is mean by interaction in MIMO system, how to, then we have seen what is the degrees of freedom. We have seen degrees of freedom only tells us how many process variable a process has. We cannot control, we cannot create more loops than the number of degrees of freedom that we have seen. Then we have seen an interaction. Then we have seen how to select a set of process variables and set of manipulated variables that we have seen. Then we have seen relative gain array. Relative gain array means so far we selected 4 process variables and we assigned manipulated variables based on qualitative analysis. That can be quantitatively analyzed. For that, the relative gain array is used. How to find the elements of relative gain array we have seen, and how to form control loops based on relative gain array we have seen. These are all the topics that we have seen in MIMO process. Today we are going to see decoupling of interaction. Relative gain array. Interaction means if one variable affects 2 process variables, then it is called interaction. We have to select the manipulated variable so that the interaction will be minimum. For that, we can use the relative gain array. If this is related with M1 and this is related with M2, this is related with Y1 and this is related with Y2, means then to control Y1, both have effect on Y1, M1 as well as M2. Whether we have to use M1 as manipulated variable or M2 as manipulated variable, so far we used the qualitative analysis. Now here we can say that quantitatively this M2 has more impact on Y1 because it has a relative gain of 0.75. That's why M2 should be used to control Y1. M1 also has impact on Y1, but it has more interaction from M2. Similarly, Y2, M2, Y2 has to be controlled by M1, not M2. This we can obtain from the relative gain array. If it is 3 by 3 matrix, already we have seen that if you find only one element, then we can write the other 2 elements. That is also possible. If 0.25 means, definitely it is 0.75. If you are able to find this, then this is 0.75 and this is also 0.75. If this is 0.7 means 0.25. One measurement is sufficient, but we would find at least 2 so that whether the selected manipulated variables are correct or not. If you find 2, the remaining 2 can be written. Then suppose if it is a 3 by 3, then this is lambda 11, lambda 11, lambda 12, lambda 13, then it will come. If you add all the elements, then also it is equal to 1. Here lambda 12, lambda 2, lambda 11, lambda 21, lambda 31, like that it will come. If you add all the elements of 3 by 3 relative gain array, then also it is equal to 1. That we should remember. Now we are going to see how to design a non-interacting control loop. Already we know that if M1 is manipulated, Y1, not only Y1 changes, y2 also changes in a 2 by 2 matrix, in a 2 by 2 MIMO system. Similarly, if we change M2, both y2 as well as y1 changes. For that, we can obtain a mathematical model. That dynamics between M1 and Y1 is represented by H11. Dynamics between M1 and Y2 is represented by H21. Dynamics of M2 with Y1 is represented by H12. Already I said the suffix, first suffix represents output, second suffix represents input. H22 represents the dynamics between M2 and Y2. Now, this is responsible for that interaction. This is responsible for interaction between M2 and Y1. So, how these two interaction can be nullified, that we are going to see today. How we can nullify the effect of H21 and H12. That is called decoupling or a design of non-interacting control loops. If we remove virtually, if we remove H21 and H12, then it is a function of H11 and H22. That is called decoupling. This how we got this y1 equal to what? Y1 is y1 equal to y1 is here we are getting error. The controller output is M1. That's because based on that error we got M1 here. This M1 multiplied by H11. That is written here. M1 multiplied by H11. Similarly, we can write M2 multiplied by H12. That is also equal to Y1. Y1 is contributed by both the effects of M1 and M2. So we can write H12 multiplied by M2. Similarly, we can write Y2 equal to H21 M1. H21 M1. H21 M1, H21 M1. So this way, H21 M1 and H22 M2. So that way we can write. What is our design idea? We want to make Y1 equal to 0 so that because of any changes in M2, we want to make y1 equal to 0 so that any changes because of M2. Then if you may substitute y1 equal to 0, we will get m1 equal to divide on both sides. This is 0. Divide on both sides by H11, you will get M1. If you bring that M1 in the left hand side, M1 equal to minus H12. That is this H12 divided by H11 multiplied by M2. If we are able to increase delta M1, it means delta M1. This is delta M2. Delta M2. Already we know that if anything, if you write in S domain, that is only small changes. It is the equation for changes that we know, and these are all equation for changes that we should keep in mind. So delta M1 equal to H12 by H11 delta M2. If something is changed in M2, that will affect Y1. Means if you create additional M1 to compensate for that. If this relation is true, then Y1, there is no changes in Y1. That is the meaning. That is the meaning. If this relation is true, then the Y1 equal to 0. Therefore, we can put a decoupler D1 equal to D1. That is delta M1. That is equal to delta M1. And the amount additional controller delta M1 it must be equal to H12 by H11 multiplied by M2 times Similarly, from the second equation, we can write that d2, that is delta m2 equal to change in m2 required to make y2 equal to 0 is h21 by h22 multiplied by delta m1. So what we can do, this is the additional controller output that must be included in M1. This a new M1 equal to delta M1. This delta M1 dash we can put to distinguish between actual M1 and this decoupler output. M1 plus delta M1. This is M1 dash. This is M1 dash. This is delta M1. This is generated by actual feedback controller there plus old value of M1. So if you add all these together, we'll get the controller output. Then it will be decoupled. You see here, D1, what we have seen, what is D1, H12, D1 is H12 upon H12 upon H11, H11, that is D1, decoupler. So give change in M2 as input here. We are getting change in M1 as output. Add both M1s together and give it to the process. It consists of here H11 is there, H11 is there, here H21 is here, here H12 is here, and here H22 is here. That we should imagine. So this is the process. This is the process. For that, if you add this, the interaction will be decoupled. In the same way, we can put another decoupler from M1 to here. So this is another decoupler. If you put these two decoupler, the interaction will be completely eliminated. If you here, if you do the block diagram reduction for this, then you will get like this. How many paths are there? This is one. If you take this alone, and how many forward paths are there? This is one forward path, and this is another feedback path. So it comes this way and it goes this way, and sorry, I will show one closed loop path for block diagram reduction. This way it comes here, and so we should not travel once again in the same path. So it is not forming a loop. Here, if you combine these two together, then only it is not a loop. It is not loop. So only one forward path and the feedback path here. So it is better to use signal flow graph. To reduce this into a single block diagram. If you do like that, you will get this. You try yourself to find this. You try yourself to find this. This will be your assignment to find this transfer function. Both are decoupled. You notice that both are decoupled. Earlier we have seen that this as a single block. Now it is decoupled. It is to prove that made like that. What you have to do is you simplify this by using signal flow graph and find the transfer function like this. Very simple. If you convert this into signal transfer function. So by applying that signal flow graph, we obtained this. From this, we can understand that virtually, but not actual, virtually these two loops are decoupled. Partial decoupling. Suppose I am having a process in that, let us see one process. In that process, let us assume that this y can be varied, but y2 should be tightly coupled. Y2 should be tightly coupled. Y1 can be varied means no need to put D1. D2 alone can be implemented to tightly control Y2. So this is called partial decoupler. You have to use D2 to keep Y2 any deviations, but Y1 we can allow to vary because of interaction. uh, Feedback loop is there. It takes long time to decouple that because of the deviation. So that is called partial decoupling. If Y1 can be varied, for example, this is a level process, that will not affect the quality of the process, then it can be allowed to vary Y1. But Y2 should be concentration composition controller. It should be tightly controlled. Means we can use this decoupler D2. That is called partial decoupling. Sometimes we'll get physically unrealizable. Physically unrealizable. Here, what is the transfer function of H11? This is H11. This is H12. This is H11, and this is H12. H12. Here in the denominator H11 is there. Numerator no problem, H12 is there. In the denominator it comes there, e power minus 1.5. If it comes here, then what will happen? If it goes to the numerator 1.5, e power minus 1.5, and it is in the denominator, so it becomes plus 1.5, and this becomes this becomes H12 having already minus 0.5, minus 0.5. If you add these two together, you will get plus 1. So it means, the meaning is it requires future value. You know that e power minus means delay. Future value is required. Future value is required. That's why it's physically unrealizable. We do not know the future value. That's why it is not physically realizable. This is physically realizable. In that case, you cannot implement D1, but you can implement D2. That's what I said here. Partial decoupling can be implemented because we are very much worried about Y2, not Y1. That's why D2 alone can be implemented.